Okay, I believe I'm recording right now. Greetings, everybody. Let's see. Last time we went over particle swarm, which was a great algorithm for performing search for decent high dimensional spaces, but not something with billions and billions of free parameters. But if you got 100, 200 parameters, the space that you want to look over, particle swarm works pretty well. And we explained that the reason that it worked well is that these birds keep flying, even though they've passed by their personal best, and even though they know where the global best is, they keep on flying. They don't kind of commit to a single value. And other algorithms like stochastic hill climbing or evolutionary sort of search do commit to specific values. And that's the reason I think the particle swarm works so well. Today, I wanted to talk about a number of issues, the first of which is each one of you has taken this course in order to learn something. And what I want to do is to give you a chance to choose what you want to learn. So what I'm going to ask you to do in 2 weeks, let's see, 1 week, I'll give a date to it, but next week we kind of have off, but the Tuesday after that, I would like you to propose to me a paper which you would like to read on, which you would like to read and report to the class on. In other words, I'd like you to give a lecture from the literature. And one of the nice things about taking graduate courses like this is it gets you up to the point where you can read the literature on the topic that we're talking about. So as you do, go to the literature, you're going to find out that you understand a lot of what's going on, maybe not down to the jot and tittle, but enough to read the paper and to understand it. So I would like you to give a PowerPoint presentation, and we will have that the last, 3 days of class, 2 or 3 days of class, where you will present what you've done or what you've read. And what I hope you do is choose some challenging papers. The hardest ones are the pure theoretical ones. The easiest ones are just pure applied ones. I would prefer that you choose a journal article as opposed to a conference paper, but in the area of AI, things are developing so quickly that some of the conference papers are really, really good and haven't made it to the journals yet. So I will leave it to you. If you do choose something which is in the area of application, make sure you understand make sure that you understand and have a domain expertise in what you're talking about. So that will be the final thing, that the final project. Then we will have a final exam. The final exam will be oral, and I will schedule those at the end of the semester. So any questions at all? We do have, let's see, when was the homework due?
I think it should be due today.
It is due today. Okay, with that in mind, let's go ahead. Let me check. I should have checked beforehand. I do believe that it's due today. So let's take a look, see. Yep, due November 4th. Okay. First thing is to prove the law of importation in Boolean logic. This, if you did it, you'll find out that, yep, it works, but you'll also, if you're like me, be surprised that indeed that it does work, because it doesn't seem that disjunctive and conjunctive reasoning would be equivalent to each other, but indeed they are. I have to get my random number generator here. Today we only have 4 people, so I only need 2 coins, which is good. So law of importation. Would anybody like to not participate in this?
Yeah, Dr. Marx,
I
never knew that. Yeah, I never knew that a due date was assigned to the assignment already.
Yeah,
so
one of the things, I mean, what can I tell you? You're not required to attend class, and some of you skip out occasionally, but you are required to keep up with the assignments. So, yeah, please get that done very, very quickly.
Yeah, I also don't notice that
There's a due homework due today.
Oh, well, let's see. Do you guys go to my infamous spreadsheet? Yeah, I'm not happy that you're not done today. Yeah, here it is in the spreadsheet. It's been here for quite some time. Homework number 3, due November 4th. You can see my screen here, right? And prove the law of importation in Boolean logic. And are there things in fuzzy control that conjunctive reasoning can do that disjunctive can't? So it looks like we're down to a single coin flip between Sam and Cullen. Okay, that's.
I think Trevor's also here.
Oh, is
Yeah, I
Trevor
am.
here?
Yeah.
Okay. Sam, Cullen, and Trevor. Okay, you're right. You're right. Sorry, Trevor. You know, Zoom only gives you a certain number on the right screen, and Trevor, you are off screen. So that's the way it is. Okay, I'm not even going to give you numbers. First one is heads. Second value is tails. That's 3. So skipping Ming Kung and innocent, that's 1, 2, 3. Trevor, you're up. Can you tell me how you prove the law of importation?
Yes. So what I did was I went through the conjunctive sense and created a giant truth table.
Yeah, that's the way you do it. Exactly.
Went through a giant truth table using the example that we've gone over in class with the 4. So it creates 16 states.
Do you have anything you could show us?
Yes, actually. Oh, you did activate screen sharing. Cool. Sure. All right, can everyone see my screen?
Yes.
Cool. So this is the first truth table. This shows the conjunctive of, or what was it? Where everything has to be ANDed together in order for it to work properly. So I know in class we use the example of turning left. So as you know, if we break the tire or if we accelerate a tire, then this results in the car turning left. And so I split this up into terms and clauses. Terms are when the result is true, and then clauses are when the result is false. And then what I did was for a clause, if it's 0, then it's just normal. But if it's a 1, then it's flipped or inverted. And so going through this truth table, you know, with all zeros, they're just all ORed together. And then going through and saying that, you know, as you add ones and you start going down this truth table, the inverted, I guess, metric tends to shift around until you get to the one where it all becomes positive, and therefore it's all ANDed together, which is what the conjunctive states.
Okay, so you're saying it's only all true if every element in there is true. Is that what you're saying?
Well, this is the conjunctive state.
For conjunctive, yes.
Yes. And so then for the disjunctive, you kind of reverse the process. So again, clause is when it's not true, term is when it is true. And then unlike the previous example, if it's in the term column, if it's 0, then it's inverted. And if it's a 1, it's not inverted. So you can see here, you have 0 for A, 0 for B, 0 for C, and 1 for D. So it's not A and not B and not C and D. And so
Okay.
going through this list here, this is the terms that we come up with. And so then when you compare the two together, you notice that for all zeros, that the kind of equation that comes out of this is equivalent. And then when you get to where it's all ones, the all the terms are equivalent for that equation that forms from the disjunctive and the conjunctive. And so then going through, you can see, you know, not A and not B and not C and D is equal to A and B, A or B or C or not D. And so going through that list, we can see that there is the law of importation for Boolean logic. You can see that they are equivalent.
Okay, thank you, Trevor.
Mhm.
Let's see, Sam Collin. Sam and Colin, do you have a different perspective on that?
I did a smaller scale truth table.
Okay.
So here, I just took importation to be the equivalence of these two statements, X and Y yields, or if X and Y, then Z, or if X, then if Y, then Z. And so for all the combinations of X, Y, and Z, so for example here, when X and Y are both true, but Z is false, the whole statement is false. And for the rest of them, either the first term is false or the second term is true. And in all those cases, the if then statement is true. And then for the other case, if either Y or X were false, then the whole statement was true. And then if Z was true, then the whole statement was true. And so these truth tables match.
Okay. Was anybody surprised that this worked? You were
Yeah, I mean,
surprised?
it wasn't apparently intuitive, but you know.
No, I don't think it is, but it's kind of remarkable that it does. So
when I
okay.
was trying to prove it, I found like kind of a direct proof.
Let's see what you have, Colin.
It may be incorrect, so hopefully you can give me some feedback on it. All right, are you able to see this?
Yes.
So here's sort of the law I was trying to prove. So I basically just converted it to ands and ors using this identity here. A implies B is the same thing as not A or B.
Oh, that's cool. Okay.
And then just using, I think I used just this definition, and then the definition of this implies, then De Morgan's, then idempotence, then the identity and the definition.
Okay, that's very nice. So you did it not with a truth table, but with direct Boolean logic. That's very nice. Very nice.
I think the one thing that I was kind of confused by is, I think you mentioned that it doesn't work for fuzzy logic.
No, it doesn't.
But using like sort of model-based min-max fuzzy logic, where we
Okay, let's
assume
take a look at this. Let's see if I'm wrong.
So yeah, I think sort of my confusion here stems from the fact that are you using fuzzy logic to denote a program or a model for something?
Well, let's see what you have. I think it's a just fuzzy memberships, whether those fuzzy memberships work or not, whether you get the same antecedent. No, not the same antecedent, but the same consequent result.
So yeah, maybe we can find the error here in this attempted proof. So what I did is I basically took this implication operator and converted it to basically its fuzzy form, the maximum of 1 minus A and B. So it's sort of the analog of the not P or Q is the same thing as P implies Q.
Okay.
So I converted that, and then of course this intersection is the same thing as the minimum. So the max of 1 minus this minimum should be this correct translation to fuzzy logic. Then I applied fuzzy De Morgan's law, which I believe we showed in a previous.
Yes, yes. De Morgan's law works for fuzzy logic. Absolutely.
And then I, what do I do here? Oh, since these are both maxes, they're idempotent. So I can sort of switch the order. And then I received sort of the exact same thing out.
Okay, looking at that, I don't see any errors, but but my experience says that your conclusion isn't right, but I can't put my finger on it. So I'm going to assume that you did everything right. See, I'm not familiar with that comma C there, comma the consequent. So I would have to study that in order to make a commentary on it.
Okay. Yeah. So like the if then statements are sort of encoded logically, not programmatically. So I think that's kind of where my confusion arises.
Okay.
Um,
Yeah. So yeah, no, well, this is an interesting take, trying to apply the fuzzy logic in order to determine that. My engineering intuition says that with the conjunctive logic, you have more knobs to turn. Therefore, you should be able to do more.
Hmm.
So let's go to the next statement. I'll have to look at this a little bit more closely. Yeah, please put this in Dropbox, and the date you put it in Dropbox is something that I can look at. So Innocent and Ming Kun, let's get those in, and I'll give you credit for a late submission. So
Dr. Marks, I have a quick comment about the importation. I had a similar conceptual difference between using a logical if then or using a kind of programmatic if this is the case then you should do this, rather than like the truth of the whole statement. So
well, we have to look at the truth table for implication. Did we go over that previously?
I don't think we discussed it in the class, but I think I hate to assume it, I think we're all familiar with.
Okay. Anybody like a refresher on the law, the Boolean law of implication?
And just to be clear, that's the if A then B, that's true if
A
ever
then
A is
B.
false or if B is true. Okay, yeah, I think Colin talked a little bit about that in his.
Yeah, okay. If both are false, then the result is true. If false implies false is true. The other two cases, as long as the implication is one, the result is true. The only time is where truth implies falsity. It's false. So I think it's a
Right. So I think
0. Yeah.
I think when Colin and I were talking about a model and programmatic, and forgive me if I'm misrepresenting your idea here, Colin. That's kind of in the logical sense, if then, but a lot of times when we try to apply control systems, we have an antecedent and we are trying to determine the consequent.
Yes.
So that's kind of perhaps a little different than just Boolean if then. It's kind of a programmatic, what should you do? Colin, help me out here if that's not what you were talking about.
No, yeah, it's kind of exactly what I was getting at. I have like a minimal example that was kind of incorporated into my answer to the second question on the homework. Would it be right if I kind of share
please
that?
go ahead and share it. Thank you, Colin.
This was sort of my attempt to try to resolve this, and I don't think I did a very good job. So essentially, like I have sort of two programs here. One sort of appears to be conjunctive, and the other appears to be disjunctive. And these two programs aren't equivalent. So this is like if A, then C is true. If B, then C is true. That's sort of the disjunctive form, and this appears to be the conjunctive form, but these two programs aren't equivalent. So in like a logical sense, where you're just trying to model the behavior of the system, then it makes sense that if I have like a bunch of things that are true initially, then this consequent happens. It's equivalent to saying that if I consider sort of all of these clauses, A sub k implies C, that essentially means that if it is true that for sort of at least one of these clauses, A sub k implies C, but it doesn't necessarily mean globally.
It has to apply for the entire truth table. The other thing, for the disjunctive, let's see, do I see the false implying false being true here?
So the reason, so these two programs look like they're equivalent by the law of importation, but if, for example, A is true and B is false, then C will be set to true, whereas C will not be set to true here.
Yeah, I think I see what you're saying, Colin, and I had a similar thought process here. I kind of reasoned with myself to think about it in kind of a fuzzy sense, where in the top program, if A and B, then you could have C is very close to 1. And then in the bottom program, if you have A or B, you could add like 0.5 to C. So if just A is true, you could have a C membership function of 0.5. But if both of them are true, you could have a 1. And I don't know how that, obviously that doesn't apply to crisp logic, because you're essentially equating an and with an or if they're going to be the same. So I also had a similar, cognitive dissonance there. I don't really know how to resolve it either.
Yeah, I think that sort of the main problematic thing here is that sort of a programmatic if-then is not the same thing as a logical if-then. In fact, sometimes a programmatic if-then is equivalent to a logical if and only if. So yeah, I think that's kind of where the confusion's coming from, like you said.
Okay. Well, thank you. Thank you both for the confusion. This is great. Appreciate it. I remember this is very interesting. When I was working with Bill Combs on the Combs control and his disjunctive logic, we had let's see. First of all, I had an argument with Bill Combs that in Boolean they were equivalent. And when I showed them in Boolean they were equivalent, he was kind of amazed. Okay. But we had an argument with another guy. Man, I can't remember his name. He was a guy from another university that said he had proved that everything you could do in fuzzy with one, you could do in the other one. And we finally convinced him that indeed that wasn't the case. So that's what I'm sticking by in terms of my memory. I wish I could remember the detailed example that we gave him, but it did turn out to jive with our idea that there were more degrees of freedom in one than another one. So that leads us to the second one. This is kind of a philosophical thing. Assuming that they're not the same, do you think that there are certain things that you could do with disjunctive that you couldn't do, or that you could do with conjunctive that you couldn't do with disjunctive?
Yeah, I had a pretty simple example that hopefully demonstrates some of that.
Okay, please.
I don't know if you're going to flip coins or whatever.
No, you're number 0.
Okay, great. Let's see, let me share again. So I kind of appealed to the cruise control that we talked about earlier. So the way we looked at it earlier was in a conjunctive sense, where, for example, if your speed error is low, but you're accelerating to match the speed, then you don't really need to do anything, because even though there's an error in the speed, the acceleration is kind of already taking care of it.
Right.
Whereas if you were to look at it in a disjunctive sense, here's kind of a sample rule table. So you look just at the speed. If the speed is above, you need to decelerate. If the speed is below, you need to accelerate. And then if your goal is also to have an acceleration of 0 when you get there, then if your acceleration is positive, you need to decelerate. And if your acceleration is negative, then you need to accelerate. And so you're looking at them independently. And so in a scenario like this, where your speed is below the target speed, but you're also accelerating to meet the target speed, because the two input variables are so interconnected, a conjunctive kind of rule table here works well, because using the disjunctive rule table, because your speed is less than the target, this is going to have you continue to accelerate until you touch the line, and then you're going to have an incredibly underdamped, if not flat out simple harmonic motion when you go up and down, just because your speed doesn't know what your acceleration is doing and your acceleration doesn't know what your speed is doing. Because they're so interrelated, if you lose information from the other, you can have poor results. And so I was trying to come up with a better example, but that's kind of the one I ended up with, where if your input variables are related enough, then that they have significant impact on the others, then disjunctive is severely limited in being able to realize those interconnected relationships.
Yeah, I think the disjunctive requires relationships among the antecedents. There has to be kind of a redundancy there. Like in the cars, they're all doing the same thing. And if you had, say, dependent sort of things, say you wanted to cool down your house, like it got too hot inside. So you would open the door and you would cool down and you would then close the door. You cannot take those three requirements and place them in a disjunctive sort of fashion, because none of those individually cools down the house, right? There's no redundancy there if the actions in some sense are independent of each other. Where if you do have redundancy, it looks like the disjunctive is the way to go. Okay.
Yeah, it seems like whoever's doing the design would need to figure out which variables are connected or not, and then they can, if they are unconnected, then that would be very good for them because they can
Yeah.
do disjunctive.
And by the way, just if you think about it, if you ever do one of these systems, you don't have to go purely disjunctive or purely conjunctive. So you have 5 variables. You can take, say you have 5 variables. You can take 3 of them, make them conjunctive, and make 2 more conjunctive and put it together by a disjunctive link, right? So you can have these hybrid sort of systems. So it isn't just one or the other. It's a combination. It can be a combination of the two. And so the ORs are between things where there's a redundancy of operation, because that looks to be a necessity in application of the disjunctive sort of rule. Like it's very transparent. And if you turn left, those different rules were all different ways that you could turn left. There was lots of redundancy in what was happening there. So that's kind of my takeaway. Any other thoughts on that? Okay, such a deal. Let's then talk about some other things. I wanted to talk about, let's see, we have not talked about ROC curves. Is that right?
We did talk about them. We talked about how for like I forget what it's called, but the Russian missile defense system, if you wanted 0 false alarms,
okay.
you just keep it off the whole time. And if you never wanted to miss something, you would just leave it on the whole time.
Okay.
So we did talk about some of the trade-offs there.
Did we talk about the literal curve?
Oh, you didn't show a picture or anything.
Yeah, I didn't show a picture. I think I'd like to kind of do that, and let's talk about this. Okay, I kind of screwed up my example, so I'm going to share my screen and kind of initiate a new thing using my notes. Okay, hopefully here you can see my PDF file here. Where do we place T on this threshold? Forget about the Fisher vector. This is the same exact problem. We set a threshold T. Above it, we have an X. Below it, we have a 0. Okay, so this is our training data. The X's can be attack. The zeros can be not attack. So where do we place the T? It depends on your desired performance. And we're going to have X being a thermonuclear attack. And see, unfortunately, I set up the problem wrong, so I got confused. X is a thermonuclear attack, and 0 is no attack. Now, in classical theory, we have hypothesis testing. H0 is that the element, and this element can either be a 0 or an X, that it's the element is equal to 0 and giving no attack. And the second one is that the element is equal to X, which is an attack. And we would like to have these two probabilities. Alpha is equal to the false alarm probability. That's the probability that there is no attack, given that the element is equal to 0. Let's take a look at that. It's the probability of H1, given that the element is 0. So it's the probability of announcing H1 given the observation that there is no attack. The detection probability here is different. It's the probability of H1 given that the element is equal to X. In other words, given that the element is equal to X. So both of them, at least the way that I've couched them here, is it's the probability that the alternate hypothesis, so therefore both of these are in this domain, right, to the right of the T. So it's the probability that H1 is of announcing H1 given the observation of no attack, and the probability of announcing H1 given that the observation is attacked. Now, it turns out, what do you think happens as this threshold increases? What happens to the detection probability as this increases? Can you see my cursor? As this threshold increases, we're going to have more and more false alarms, aren't we? As this threshold increases, we're going to have more and more false alarms. As this threshold decreases, we're going to have greater detection. We're going to have greater detection, right? So as this increases, beta goes up. The detection probability goes up, but the false alarms also go up. I'm sorry, I did it the wrong way. As we go to the left, the detection increases. I'm thinking of thermonuclear attacks now. As this gets smaller, do you agree that the detection probability increases? And as this gets smaller, the false alarms will also increase. Let's try it again. I'm not doing a very good job, am I? Clearly, as this threshold becomes much, much smaller, the more the attacks get classified correctly as attacks, right? As this gets smaller, then more and more data becomes attacks. So our detection probability is going up, just like we always left the detection light on. But also, as we go to the left here, we get more and more zeros in there. So we get more and more false alarms. So as we go to the left, the detection probability increases, but the false alarm probability also increases. This is inherent in all detection design. As the detection probability goes up, the false alarms go up. It's a classic trade-off, and you can't have both. What you would like is you'd like to have the best decision that you possibly can, but this can be performed as, well, this can be viewed as follows. As the T changes, the false alarms and the detection probabilities change, don't they? So at this T, there's going to be a certain detection probability and a certain false alarm probability. As I move it over here, the detection and false alarm probabilities are going to change. And so I can plot a parametric curve, which I do right here. And in all of these cases, we have a false alarm versus a detection probability. And for a given value of T, this is the false alarm, and this is the detection probability. And as we begin to increase T, we begin to go down on this curve. This curve then is your trade-off. And it tells you the trade-off that you can have between the detection probability and the false alarm probability. Now, what do you want to do? There's no best solution. You only have a trade-off. This is ubiquitous in engineering design. And this is the problem that you get in when you're interpreting the output of a neural network, and you want to go between the idea of a high detection probability or a high or a low false alarm. You can't have them both. This is referred to as an ROC curve after its initial use, I believe, in the military, and it stands for the receiver operating characteristic. So the idea is that you had a radio, you got some sort of signal, you have to decide whether that was a good signal or a bad signal. And this is the trade-off between the two. So let's take a look at how we would assume this empirically.
Sorry to interrupt, Dr. Marks. I have
Yeah.
a quick question about
Sure.
that graph here. So as t goes to negative infinity and we go up and to the right on the curve,
Yeah.
do both beta and alpha hit 1? Would that depend on the probability that any given event is an attack or not attack?
Well, no,
Like-
what you're doing for beta is equal to 1. It's up here. Yeah, I hope you can still see my
Right.
cursor here.
Yep.
If you're up here, you're assuming that you have 100% detection probability. But that means all of you're also incorrectly announcing all of your no attacks. So
Right.
your false alarm also goes to 1.
So the false alarm probability is predicting that it is an attack, given that it is not an attack, right?
Yes.
So let's say that your t is at negative infinity and an event happens that is an attack and you classify it as an attack.
Yeah. If given that it is an attack, you'll
Right.
always detect it. Given
Right.
that it's not an attack, you'll never predict it.
Right. So I'm just having trouble wrapping my head around the false alarm probability getting to 100, because if a real attack happens and you classify everything as an attack, then that's not a false alarm. So your false alarm probability is less than 100. I mean, I get that it's really high.
Yeah, I'm not saying that. No matter what
Okay.
happens, you're going to say it's an attack. So
Right,
you
but
always
if
you always make a
Right.
mistake. 100% probability, you goof.
Unless it is an attack, then you're not making a mistake, I guess.
Well, don't forget these are conditional probabilities.
Right.
One is they're both conditioned on H1, and the part before the H1 is whether you're being attacked or not attacked. So they're conditional probabilities.
Okay. I think I figured it out. Thanks
Okay.
for remembering me.
Okay, let's take a look here. Here's an example. Okay, of a point on this curve. We have a bunch of zeros and a bunch of X's. Now, what is alpha? That's the false alarm probability. That is the probability that you choose something above the threshold, given that you're not being attacked. So that would be 1/5, since there's 5 points here. Your beta, on the other hand, would be, okay, you have 4 points, 3 of them you classify successfully, the 4th you don't. So your detection probability for this threshold is 3/4. So therefore, if we were to go to ROC curve, we would go to alpha is equal to 1/5 here. And then we would plot beta is equal to 3/4. This again is a parametric curve, which is parameterized by the threshold. Now, if you are a person that likes to think of probability density functions, this is a better way of doing it. We have 2 distributions. One is for the null hypothesis. The other one is for the H1 hypothesis, okay? This is that you're not being attacked. This is that you are being attacked. You set a threshold. Alpha is equal to the area under the curve here for the H0. Beta is equal to the area under this H1 curve. So if you do have the probability density functions available for the 2 hypotheses, this is the way you would do it. The relationship above right here is how you would do it empirically if you had raw data. Down here is if you had the overall density functions, how you could perform that operation. So with this in mind, let's suppose that we had an ROC curve. You design a detector, I design a detector. We come and we do a test of your detector on test data. Okay. Now, let me go ahead and erase everything because I really screwed that up. Now, we have the 45-degree line here. By the way, the 45-degree line corresponds to you flip a coin. You make 50% detection, you make 50% notch detection. So all of these curves go between 0 and 1. So here we come in, and here's your curve. And we come in, and here's my curve. Whose detector is better? The blue or the red?
It's the
Wouldn't
blue.
you need? Okay.
What's that?
Oh, sorry. Was someone else answering?
No, go ahead, Colin.
It's the blue one, the one that has the greater area.
Yeah, the blue one is because for a given false alarm, you're going to have a better detection probability, right, with the blue than you do with the red. So definitely the blue is better. Now, if you ever take a course in statistics, you'll find out that in certain hypothesis testing, there is an optimal curve. That is, there's a curve which you can't get above. This is called the Neyman-Pearson optimal detector, Neyman-Pearson optimal detector. And it is a detector which for a given alpha maximizes beta, and you can't do any better. Unfortunately, these curves are very rare. They're very specific. And in general, you're not going to know which detector is better than another one unless you test it. Now, what about this curve? Here's one curve. And here's another curve. Both of these are supposed to meet at the top at 1, 1. Which one's better here? Which one would you choose? Or if you're not sure, which would determine which one you choose?
So looking at the regions where one is above the other, so the area where the blue one is above the red one looks to be less than the area where the red one is above the blue
Okay,
one.
that would be an
So-
overall global. No, you're right.
Right.
You're saying that this area is better than this area. I guess the answer that I was looking for. Sometimes professors ask questions and they have an answer in their head, and no one knows what that answer is. That we're asking you to guess it. That was kind of like this question. My answer would be, it depends on your operating characteristic. If you wanted to operate in this area of false alarm, you would use the blue detector. If you wanted to operate in this area of false alarm, you would use the red detector. Whoop, that's supposed to come down, right? So it depends on your performance that you want. And don't forget, this is an operating characteristic. You have to make a decision. You have to choose a point on these curves according to your engineering judgment. And that's what these Pareto trade-offs are. They're exercise of engineering judgment on your final design and what is more important than something else. Okay. So that's the answer that I would want. If you're operating up here, you would want to use the blue curve. If you're operating in this, and in a similar fashion, if you were using detection probabilities in this range, you would use the blue curve. If you were using detection probabilities in this range, you would use the blue curve, right? Or no, the red curve. I think I got it opposite. Let's see, here you would use the red curve. Yeah, here you would use, no, here you would use the blue curve. Here you would use the red curve. Okay, so it depends on what you're doing. And this is something you will hear of if you study radar enough. You will hear CFAR radar. And this stands for Constant False Alarm Radar. In other words, what they want to do is they want to operate with a fixed alpha. Now, this alpha bound is a performance criteria. And if you go below that bound, you're okay, right? Because if you get fewer false alarms, that's okay. I probably drew it on the wrong side. So let me draw it over here. This would be the alpha CFAR, constant false alarm rate. So you have to build your radar so that it has this constant false alarm rate or an alarm rate which is lower than that. And clearly what you would want is you would want to design a detector that was that bulged more than anything else. You would want to choose a detector that bulged more than anything else, than any other detector. So that would be the competition in the design of such a radar. Okay, sorry I muffled up the lecture on the ROC curve, but I hope that we were able to muddle through it here.
Dr. Marks, could you talk a little bit more about in the right graph, you mentioned the operating region. Could you talk about what that means practically, how that works?
Well, let's just,
okay,
just remember the big takeaway here is that the more bulgy this is, the better. So the blue curve is better than the red curve. So you want to always choose the curve that's on the top.
Right.
So in this case, you always want to use this part of the curve because that's the bulge that's on the top. In this section of operation, you'd always want to use this part of the curve.
Right. I get that.
Yeah.
So when you say section of operation, like in the region on the right of the dashed line where you'd want to use I guess that'd be the blue curve. Like, how do you know which region of operation you're in? Is that something you choose, or is that a given based on the problem?
Well, this is like everything in machine learning. You have to have some sort of estimation of this. How do you get an estimation of this? Well, in the case of a neural network, you would get an estimation of this from your test data, your validation data, if you will. And you would get an empirical estimate of what these curves look like.
Right. Never mind. It's difficult to word my question, I guess.
Well, I would probably have a difficult time wording an answer then, I suppose. So that would be good. So let me ask you this. Suppose that we had this curve that we talked about before. Remember, there was a line and there were zeros and X's here. Do you remember that? We said over here, we have 100% detection probability, but we had 100% false alarm probability, right? Over here, we had just the other extreme. And as we move this threshold along this line, as the threshold moved from, say, this point to this point, what always must happen? Well, let's take it the other way. If you moved it this way, what must always happen? Your detection probability is always going to go up, right? As you move from this threshold, if you move from this threshold to this threshold, the detection probability is going to go up. Do you agree with that? Also, as you move from this point to this point, the false alarm probability is going to also go up, correct? So that means as a function of threshold, you always have to have a monotonically increasing function. In other words, this ROC curve always has to be something which is increasing. Right? Always has to be increasing. Now, what happens here as the threshold goes up? The threshold goes up and your false alarms and your detection probabilities stay the same. In fact, you're only going to have certain points on this ROC curve from your data, correct? Depending on whether these X's and O's go. And let's see. I forget this. It's a stair step function. I believe it's kind of like this. It always must be like a piecewise stair step function as you begin to traverse the threshold as it begins to decrease. So the best you can get is a staircase sort of estimation of what's going on. Okay, any other questions? So the ROC curve is important in a number of different areas. It is the tip of the iceberg in terms of Pareto optimization, which is that we have a number of different criterion. And Pareto is applicable, for example, to cheap cars. Let's see, do I want to do cheap cars? Let's do cheap cars and safe cars. Now, if you want a safe car, that is, you want it high in value, then you'll probably have an expensive car, right? You'll need a Lamborghini or something like that. Do you agree with that? If, on the other hand, you want a less safe car, then it'll probably be less expensive. And if you want a less car, you'll get even less expensive. And down here is, this is a Humvee, and down here is a scooter. Right? Scooters are cheap, but they're not very expensive either. So what you will have, if you look at all vehicles, you will get something which looks like this. You will get a bunch of dots all over the map. What do you do with those dots? Well, you connect the dots on the outer edge. So the best you could do is connect the dots like this. And what the black curve shows is that for a certain degree of safety, that this is the best car you can get. There might be also some other cars that are less expensive, but are just as safe. And I did this wrong again. Let's do cheapness. I guess I wanted cheap, right? Okay, so we have safe cars here and cheap. I meant cheap. So scooters are cheap, but they're not safe. Humvees are not cheap. Wait, did I have that right? Help me out here, guys.
No, I think you had it right.
I think I had it right. Okay.
If it was expensive, then you would want to get the lowest that you could on the Y dimension. So I think it should be
Okay.
cheapness.
Okay,
But,
so this is good. But anyway, do you see the point that this is something which is called the Pareto frontier? And usually in this, it doesn't look right. Pareto frontier. And usually in design, you want a point upon the Pareto frontier. You have to decide which trade-off that you have. Yeah, I had it right. Shoot, I don't know what I was thinking. Yeah. You want to have, you have to decide which one of these that you're going to choose. It is a design decision made by the engineer or the end user, or maybe in the battlefield, a commander and whatever, and you have to weigh the risk and reward and the different payoffs that you have. Notice that we've only done this with two variables, right? Here we have safe, we have expensive, and you might have another axis here, right? What would be another axis in buying a car?
You could say style.
Yeah, that's hard to quantize though.
True, true.
Miles per gallon.
Yeah, okay, miles per gallon. Okay. So that would give you data in 3 dimensions, right? And you would have the equivalent of a 3-dimensional Pareto front there, wouldn't you? So you can see this becomes complicated when there's trade-off among different values. But in neural networks, at least for a one output, we only have to determine whether we're doing well or not doing well. Okay, any questions at all?
So in that general case where you have sort of more than one variable outputted,
Yes.
are there some metrics that you can kind of optimize to that sort of maybe attempt to maximize sort of the volume under that Pareto trade-off?
You know, it depends. It depends. If you're trying to optimize in accordance to areas, then you could do that. Usually, though, you only have a single decision to make. You have to choose one of those points. You don't have the luxury of choosing some sort of area or something like that. If you wanted to supply a subjective measure to one of these ROC curves, you could possibly do that. Okay.
Okay.
But no, I know of, I'm sure that there's different ways to assess metrics, but I think in terms of application, you come down to a single measurement and a decision. So what does that look like in 3, what does that look like in 3 dimensions? Let me go back here. You know, if you think about this in 2 dimensions, this is 2 dimensions. How do you get this Pareto frontier? It's kind of a convex hull. Imagine these are nails sticking out of the board, okay? And I'm going to put a nail here and a nail here just for grins. If I take a rubber band and I snap it around here, that rubber band will conform to the Pareto frontier. Do you see that? If I take a rubber band and go snap it, and all of those are nails, it will be where the rubber band collapses. That's a good way to visualize it. In 3 dimensions, it's kind of taking saran wrap and putting it down tightly against all of those nails, and assuming that the nails don't puncture the saran wrap. You have piecewise linear planes connecting everything, and that would be your empirical Pareto front. It's called a convex hull. And it does turn out that if you ever take a bunch of nails and you snap a rubber band around it, that the resulting rubber band is going to define a convex function, or a convex region, not a convex function, but a convex region in space.
So in the general case, like if you wanted to actually quantify the different kinds of errors, maybe assign like a weight to the different kinds of errors, like you'd have like, would that be n squared minus n different kinds of errors? That you'd have to sort of
Yeah.
manage
So
the-
that's another question. Colin is asking, what if you have H0, H1, and maybe H2? Is that what you're talking about?
Yeah, I'm picturing like if you have sort of the confusion matrix that on sort of the entries in the x-axis are the actual values and the y-axis
Sure.
are the predicted classes. You know, could you look at the values in the off diagonals and maybe try to get a measure of how, you know, what the overall, I don't want to say classification accuracy, but something
I
kind
don't
of
know,
like
off the top of my
Yeah.
head, it seems like the elements for an ROC curve can be obtained from a confusion matrix because you're only looking at the diagonal information, and then anything off diagonal is an error. So I think you can get the ROC curve from the confusion matrix in 2 dimensions, maybe in higher dimensions, but I can see in 2 dimensions that you can get the ROC curve directly from that. But I don't think you can go from the ROC curve back to the confusion matrix because the confusion matrix has different types of errors. Okay, any additional questions? Okay, thank you, everybody. Be of good cheer. Bye-bye.